Welcome to this 14th lecture video for Physics 4A. Now that we have introduced energy and momentum and looked in detail at the conditions which lead to conservation of these quantities, we are ready to look at a very particular type of physics problems, collisions. If you are thinking, collisions, how often are we going to need that? My answer is very often. By collisions, I mean any kind of physical process which occurs for a limited duration of time involving two or more objects. It includes what you would call collision in everyday language. And it includes many other processes where you don't see things literally colliding. For example, a gravity-assisted flyby, aka gravitational slingshot, over space probe with one of our planets. If it involves multiple objects and the duration of interaction is short, we can find a way to model it as a collision. In addition, many fundamental physics research activities, like high-energy particle physics experiments, are structured as a study of collisions. If you go into upper division physics studies and beyond, you will see theories and models for calculating collisional cross-sections in quantum mechanics and beyond. For this lower division class, we use collisions as our first application of principles of conservation of energy and momentum. We will start by describing the types of collisions you will see in this class and a couple examples analyzing these types of collisions. A warning: elastic collision analysis can be algebraically difficult because of the squared quantities in the kinetic energy conservation equation. There is one mathematical shortcut that we will teach called relative velocity relationship, and you will see the derivation of the relationship in one of the following lectures. Finally, we will end this set of lectures with a homework question. You have actually seen the math part of this question before, as part of the lecture 10 set. In this set, you will see the whole problem-solving approach. In the next lecture set, we will look at a wide range of physics problems which can be solved by application of conservation of energy and momentum, and when necessary, standard strategy. So we spent a lot of time going over introducing energy, work, try to say it in the right order, energy, work, momentum, and impulse. We spent a fair amount of time talking about how energy and momentum are conserved. So now what we are going to do is we are going to use those facts that energy is a conserved quantity and that momentum is also conserved under various situations to work out some problems. Let me write down a few things as a reminder of what we have covered so far. So I won't write down all the energy formulas. I'm hoping you are beginning to memorize it. But what I want to write down is for conservation of energy and momentum. There are certain conditions that have to be met. We went through this for energy in detail last time, so let me just write it down. So for energy to be conserved, so conservation of energy happens when non-conservative forces do zero net work. And I want to emphasize once again that this is the statement. I tried really hard to make this statement concise. So every word here matters. It matters that it's the non-conservative forces that you are worried about. And it matters that you can have non-conservative forces as long as they are not doing net work. So it's when you have non-conservative forces doing non-zero net work that energy, mechanical energy may not be conserved. With the momentum, I guess this is what we said last time, so I'll write that down for now, but I want to refine it a little bit later. So conservation of momentum happens when
So what was the type of force that we worried about when it came down to conservation of momentum? External forces. So conservation of momentum happens when net external forces is equal to 0. And I want to refine this a little bit because there will be situations where you clearly have external force, but we will come up with some excuse to say we can actually consider momentum to be conserved. So I will refine, so let me put a little asterisk here as a reminder that I'm going to be refining this in a little bit. So these are the conservation conditions. And so this will come up, this will be more important probably on next week, Tuesday, when we are doing general problem solving. So one of the first things you have to do is figure out is energy conserved or not, and is momentum conserved or not. And so the first thing I should talk about before we get to Newton's cradle is some of the vocabulary words about collisions, because I never properly did it. So let me spend a couple minutes just covering the vocabulary words about collisions. So it comes down to what we call types of collisions. And there isn't really much to it other than knowing the words that we use to say a particular thing. So let me call it types of collisions. So there are three main types of collisions. And there's really only two words that have to know. The two keywords that you have to know are elastic and inelastic. But why am I saying there are three types? With the inelastic, we introduce one more thing that we call completely inelastic. We briefly touched on this for the purpose of being able to do your lab on Tuesday. So I just want to tell you what the description of these are. And I guess the most important word here is the word elastic. Because once you know what elastic means, then the rest kind of makes sense. Anybody here know what elastic means? Like, if you just heard the word elastic, what do you think of? Rubber band, something that stretches and something that's bouncy, right? So when you have something that's bouncy, or golf ball is surprisingly elastic. In fact, if you cut it open, there's like rubber bands inside. That's what I hear. I haven't done it, but that's what I hear. So it's got elastic material in it, and with something that's elastic, this is what you see. That compare a golf ball with something that's not going to be as loud. I'll do steel ball. So compare this golf ball with a steel ball. When I drop them, all right, they're all loud. Steel ball, goes to zero pretty quickly. Golf ball bounces a little bit more. So what I want you to associate with the word elastic is conservation of energy, in particular conservation of kinetic energy. So that will be the definition that will hold through almost all your classes, even in like particle physics. When people say elastic, they are talking about total kinetic energy being conserved. So that's what elastic means. So it means kinetic energy is conserved. And once somebody says that a collision is elastic, then you kind of leave it to the person who said the collision is elastic to establish how the collision is exactly going to be elastic. So if I tell you the collision between these two carts is elastic, then you leave it up to me to exactly set up the situation that will make it elastic. So in this particular case, it almost works without the track. In this particular case, the way it's made elastic is I put magnets here that repel each other, and they interact with each other in such a way that there's very little loss of energy. So that's how I made it elastic. Or I could have done it with the springs. Or it could be like a collision with this. It doesn't look like there's any springs there, but there's some mechanism there that makes it elastic. So that's why it's important to know what these words mean, since once someone says elastic, they can now assume that you know that this means kinetic energy is conserved. Yep. All right, so what do you think inelastic means? Yeah, kinetic energy is not conserved. In fact, inelastic means not elastic. So let me actually just write it down that way. So it means not elastic. So it means kinetic energy is not conserved, apparently. And, and when we say something is elastic, it's a bit of idealization. It's like me saying that this cart slides without friction. It's not 100% true, but I'm asking you to ignore friction. Even this golf ball, which I described as earlier as elastic, well, when you look at it too closely, you'll see that it's not really elastic. If it were truly elastic, it would bounce and come back to this exact same point. But it doesn't. Nothing that you have is ever perfectly elastic. But so when we say the word elastic, we are saying, okay, assume that. When we say something is inelastic, this is really all we are saying. When we say something is inelastic, we are saying, all right, no longer assume that kinetic energy is conserved. This describes the vast majority of processes that you will see in real life. And what I'll tell you is that this is the least helpful as far as problem solving goes. When I tell you something is an inelastic collision, essentially all I've told you is that energy is not conserved. So if you were hoping to use conservation of energy, I'm telling you, all right, you can't use conservation of energy. But I haven't given you any useful information beyond that. So if you want to, whenever a problem says that some process is inelastic, I will have to give you additional pieces of information. Like in the case of this golf ball, I have to tell you with what speed it's bouncing back. Otherwise, you have no way of figuring out. So if I told you to assume this is elastic, then you can assume whatever speed it's coming in with is the same speed it's going out, right? But if I tell you it's inelastic, then essentially there's a large range of possibilities. This golf ball, after dropping, it could actually get stuck and just remain there. That's the least energy it could have. Or after bouncing, it could come very close to elastic, but 99% or something like that. So inelastic covers the huge range. So when I tell you some collision is inelastic, I essentially have to tell you additional information, or you can solve the problem. It's an underdefined problem. So which is why we introduced this additional category, completely inelastic. So what do you remember from what we covered about completely inelastic on Tuesday? Like, what do you look for to say that a process is completely inelastic? Stephen? Not all kinetic energy is lost. So let me give you an example of a completely inelastic process. So this is an example of completely inelastic process. Let me take these two cards. Okay. So I have arranged the magnets so that one way they repel, the other way they attract. So this collision that you will see now, this is a completely inelastic collision. Now, was all kinetic energy lost? No, right? It continued to move after collision. So now, actually, there is a law of nature that prevents me from getting rid of all of the kinetic energy. Any guesses what that law of nature might be? Law of conservation. Conservation of what? Because I'm saying that, okay, once again, total energy is conserved, but in this collision, as much as possible, I'm going to get rid of mechanical energy, turn you into thermal energy or whatever. But what I'm saying is that there is some other law that doesn't concern energy that actually says I can take all of the kinetic energy away. I have to keep some part of the kinetic energy. It's within something that we already covered. One of the laws of nature that we have covered, one of its implications is that in a collision like this, I can't get rid of all the kinetic energy. You could say Newton's third law, or you could say conservation of momentum. It means the same thing. Yeah. So because I have to conserve momentum, in this collision, so when I was holding onto this cart, there was external force, I could get rid of all the kinetic energy. But when I wasn't holding onto it, there's no external force, momentum must be conserved. So I have to conserve enough of the kinetic energy to allow me to conserve momentum. Okay? Now, but Stephen, your intuition is correct in that, so within the constraint, in completely inelastic collision, you lose as much energy as possible while still conserving momentum. So that's what happens in completely inelastic collision, but that won't be usually the condition that's given to you. There's the other condition that we usually use to specify completely inelastic collision. Sometimes, never using the words completely inelastic collision, but by specifying a situation like that, you figure that, okay, this is completely inelastic collision, I know how to handle it. What's the one condition you would look for? I mentioned this on Tuesday, probably in the lab section, maybe. Yeah?
They collide and then they stick together.
Yeah, and then they stick together. So it turns out that type of collision where two things stick together and move together is the configuration where I lose as much energy as possible. So if these two carts were coming towards each other, then they actually do reach zero kinetic energy. Because I started out with zero total momentum, so it didn't have to conserve any. This conserves momentum. So that's what you look for with completely inelastic collisions. So I might even use this as the definition of completely inelastic collision, that colliding objects stick together. And one of the properties that's useful to know is that in the completely inelastic collision, maximum possible kinetic energy is lost. In general, not all the kinetic energy, but maximum that you could lose while conserving momentum will be lost. Okay? So these are the phrases we use to describe different types of collisions. And both with the elastic and completely inelastic collision, often if I just give you the initial condition, there will be enough information for you to solve the rest of the question on your own. With the completely inelastic collision, the part that's giving you the necessary information is the fact that they stick together. So when they stick together, they have same velocity. And because after they stick together, they'll be moving together. And it turns out this condition is enough to give you all the necessary information to do the rest of the question. In fact, that's what you guys had in the ballistic pendulum problem. So you knew that the collision was completely inelastic because the ball got stuck in the catcher. And I didn't have to tell you any other information for you to go from either the initial velocity to the final velocity, or from the final velocity to the initial velocity of the moving ball.
And so I do this demo with the cart. One cart comes in, strikes, comes to a stop. Second cart moves forward. That's sort of what you see here. It's an elastic collision, 100% elastic. And I can show even the values of kinetic energy. So, okay, let me just show the total kinetic energy. You can see that before collision and after collision remains the same. Now, as we reduce the elasticity, let's say to 70%, you will see that some aspect of this collision changes. For one, the ball one doesn't come to a complete stop anymore. So the fact that the ball one came to a complete stop before, that is a feature of an elastic collision involving very specific setups of the same masses, the target ball at rest, head-on collision. When all those conditions are met, then ball one stops. But you mess up any of those conditions, like the elasticity, you don't have that anymore. And you see the kinetic energy going down. Now, so let's imagine you one needed to make this completely inelastic collision. Then, this is my third question. When the collision is completely inelastic, after the collision, what will the kinetic energy be? Should it be zero or should it be greater than zero? And um, if you're thinking, yeah, if it's completely inelastic, shouldn't the kinetic energy after collision be zero? I want you to hold on to that and test it against what you see. So let me run the simulation. And that is what you see. After the collision, kinetic energy didn't quite go to zero. I think the value of kinetic energy we have right now is super inconvenient. Let me see if I can. Okay, let me make it even. Okay, let me do the collision again. Yeah. So the kinetic energy doesn't go down to zero, goes down to half. So why are we calling this completely inelastic rather than um, 50% inelastic? And strangely enough, if you made it 50% inelastic or 50% elastic, then kinetic energy actually doesn't go down to 50%, because in this particular setup, when this goes down to 50%, that's completely inelastic. So I want you to think about this in terms of constraints, the constraints on this interaction. That's really what conservation laws are about. Conservation laws are putting constraints, boxes, around what this interaction can change and what it can't change. So when we say a collision is elastic, we have set it up so that kinetic energy cannot change. And under the constraint, apparently this ball one needs to stop. As we make this inelastic, we are, in some sense, removing a constraint that energy must be conserved. And depending on this percentage now, it determines what the final kinetic energy will be. But there must be some additional constraint, because when we said elasticity is 0%, perhaps what we would have liked to see is that this would be the kinetic energy would go to zero after collision, but it doesn't. So we should think of what other constraint is there that in a completely inelastic collision, the kinetic energy doesn't go to zero. So let's start by analyzing this elastic collision first, and then we'll modify it for the inelastic collision to consider, okay, what constraints are we getting rid of, and what constraints still remain. So let me do that. Let's just start out with analysis of elastic collision. So we are imagining a setup like this, where mass M2 could be any other mass. It doesn't have to be the same as M1. And so this is the before collision. Let me label it and label some of the quantities so that I can write down my mathematical equations when I get there. So this is before collision. So the balls have some mass, M1 and M2. And the ball 1 has some initial speed. Let me call that V naught. So after the collision, they have some different things going on. We still have the same masses, so let me not label them again. But the two balls have velocities. Let me label them V2 vector, and let me label this a V1 vector. I'm going to deviate from the way I like to write my equations normally. Normally, I like to write my equations so that the quantities I write down are expected to be positive. Let me break from that tradition for this analysis and let my quantity, especially V1, be a vector. As you have seen, V1 could be positive, pointing to right, or it could be negative, pointing to left. And I will write my equations in such a way so that if V1 comes out to be positive, then it's pointing to right. And I will just let that be. And if after some analysis steps, if I arrive at negative V1, that'll indicate to me that V1 is leftward. So I'll leave V1 and V2 as a vector quantity by letting their signs remain. So that's the interaction, and this is the interaction that we are hoping to analyze using conservation law principles. So when you're using conservation law, you go through steps that's similar to this. You start by first identifying what quantities are conserved, because the general approach in conservation law strategy will be that after you identify the conserved quantity, what you can set up is you say conserved quant at some snapshot 1 is equal to conserved quantity, the same quantity at a different moment in time, because this is what it means for the quantity to be conserved. It doesn't change after or through an interaction. So with an elastic collision, you have one conserved quantity given to you. The moment someone tells you it's elastic, you are told that kinetic energy is conserved. So with the information that kinetic energy is conserved, you can write down this expression. You can say kinetic energy of the sum of kinetic energies before collision is equal to the sum of kinetic energies after the collision. So let me write out the expression. So in the before picture, only the mass m1 is moving. So it must have kinetic energy of 1/2 m1 v naught squared, kinetic energy of m1, and the m2 is at rest, so it's not moving, no kinetic energy, 0. After the collision, you'll have these kinetic energies. Kinetic energy of m1, it's gonna be v1 squared, so I guess for now the sign doesn't matter. 1/2 m1 v1 squared plus the kinetic energy of m2, 1/2 m2 v2 squared. Now, as you look at this expression, I hope you know this, that assuming that all the quantities in the initial setup is given, that's kind of typical. You have two unknowns. You have V1 that's unknown, and you have V2 that's unknown. So with the two unknowns, you need more than one equation. And this is the classic sign that you are missing some bit of information. So you've used the fact that kinetic energy is conserved, but there must be something else that you need to bring in order to have at least two equations for the two unknowns. So this is where you need to look through, think through, read about collisions again. And the important thing about collisions is that the things that we describe as collision is that as this interaction happens, there's a lot of internal force between these objects, and external forces are either 0 or negligible. So this is the classic setup that leads to your saying that, momentum is conserved. And once you can say that momentum is conserved, that gives you another equation that you can write down. You can say that the total sum of the momentum before collision is equal to the total sum of the momentum after the collision. So, okay, I need to write that down. Let me write down the expression for momentum before collision, m1 v naught. And I'm letting the sign of these velocity variables indicate the direction in this one-dimensional setting, plus the momentum of ball 2 is 0 because it's not moving. After the collision, so I'm going to write just m1 v1 And if somehow in the situations where ball 1 bounces off to the left, then V1 will be negative. So this whole quantity will be negative in those cases. So this is where I'm breaking with my usual convention, where I would have put in a minus sign here so that V1 will be positive value. I'm just letting V1 be vector. It might be positive, it could be negative depending on the situation. I'll just leave it in this form. And there's kind of a vector-like thing there. Okay, so that's the momentum of M1 after collision, and I need to add the momentum of M2 after the collision. So this is my second equation. As you carefully look at it, hopefully you notice, no more unknowns. I haven't introduced any additional unknowns. So I have a second equation, two unknowns. I should be able to solve it. So let's do that. I guess let me solve for V1, and I'll leave solving for V2 as an exercise for you. And so once I've decided that I want to solve for V1, then paradoxically, what I need to do is I need to solve for V2. More specifically, my immediate next step goal here is to eliminate V2 from my system of equations. And the way you eliminate it is you eliminate V2 through substitution. So in order to use substitution, you need to have an expression for V2 in terms of all the other quantities. So I can see here in my equation 2, I can solve this for V2. So let me do that. So when I do that, this is what I end up with. V2 is equal to, let me scroll down a little. I'm going to move the other term over. So I have M1 V0 minus M1 V1. And to get rid of M2, I divide through by M2. So divide by M2. Okay, that's the expression for V2. And I use this to eliminate V2 from all my other equations. Well, from my equation 1. So I can write down my equation 1 prime, which will be the same equation I had before. 1/2 M1 V0 squared is equal to 1/2 M1 V1 squared. And now here, plus 1/2 M2. Instead of V2 squared, I'm going to plug in this quantity. Yeah, not pretty. M1 V0 minus M1 V1 over M2 squared. And I will tell you before I go on further that it's not going to be pretty. And the biggest thing that should get the blame is the square in my kinetic energy expressions. That has potential to really complicate my algebra. And what I'll just caution you with is as you try to work through this algebra, you might sometimes face this situation where you seem to be stuck. You just you don't know what you have done wrong, but you're not quite getting to the value you want to get to. And when something like that happens, be willing to just stretch out the work and start from scratch. Go some other way. Because when you're doing problem solving, sometimes there are cases where you haven't done anything wrong, as in you haven't made any steps that someone can point to and say, oh, that's not right. Like you might not have done that, but even then you can get stuck in some blind alleys, dead ends. So, and in those cases, sometimes the best and most productive thing to do is just to scratch it out and just try redoing it and maybe trying different route. So I have edited out about 6 minutes of algebra resulting in the screen shown, where although nothing is technically wrong, it appears obtaining a simplifying our result appears to be challenging. In the remainder of the video, you will see a second approach work out better. In addition, in a later separate video, I will show derivation of a relative velocity relationship equation which greatly simplifies the algebra steps of elastic collision analysis. Now, back to the rest of the video. So I think I'm going to take my own advice. Even though I can try working through this, simplifying it, try to get a sense of what V1 is, I have a sense that that's not going to result in an expression that's very illuminating. So this is what I mean. Be willing to scratch out your work and just to redo it. I'm just going to go all the way back to the beginning and just change my mind. Instead of eliminating V2, even though I want V1 in the end, let's just eliminate V1 first. Maybe that'll result in a more manageable expression. I don't know if that'll be the case, but I gotta try it out. Yeah, so let's redo it. So even though I'm saying I want V1 in the end, I'm going to write down and choose to eliminate V1 first. Let's see what we get. So let me go through basically the same set of steps, except where one fork in the road where I have taken a right before, I'm going to take a left now. Instead of solving this for V2, I'm going to solve it for V1. So solving it for V1, I get this. Okay, I move V2 over, I divide through by V1, I have V0 minus M2 divided by M1 V2. Okay, so let's use this to eliminate V1 from my equation 1. And I'm going to come back to this because eventually I will want a value for V1. So I'll come back to it, but later. So just writing out what I'm going to label my 1 prime. So my equation 1, just eliminating V1. 1/2 m1 v0 squared is equal to 1/2, okay, m1, and instead of v1 squared, I have this expression, v0 minus m2 over m1 v2 squared, plus 1/2 m2 v2 squared. And you could be excused in thinking, isn't this the same deal as before? We still have these squares and things are still going to get complicated. But I have a bit of experience with expressions like this. I think something is going to magically simplify. So let's just work through it and see. I'm going to expand this out. So expanding it out, what it'll be, so it's a V0 minus M2 over M1 V2 times itself, V2. So you have V0 times V0, you have V0 squared, and so on. So let me just write it out. I have 1/2 M1 times V0 squared, and then I have this term here. So that's going to be plus m2 squared over m1 squared v2 squared. Okay, and then I have cross terms, v0 times that and this times v0. They are going to result in the same product. So I'll say minus 2 m2 over m1 v0 v2. Okay, that's my first term. And then I still have plus 1/2 m2 v2 squared. And I hope now as you're staring at it, you see some magical cancellation. I have this term here, 1/2 m1 times v0 squared. That's identical to this on the left-hand side. They are going to cancel. Okay, then with the cancellation, let me just distribute this and write down a simplified version. I have 0 is equal to 1/2 m1 times this term here, so that'll be 1/2 m2 squared over m1 v2 squared. okay, minus, I have 2 times, okay, so 1/2 cancel, m1 cancel, so I have a minus m2 times v naught v2 plus 1/2 m2 v2 squared. Now you might think, isn't this the same as before? You have still squared terms and linear terms, but watch that you have 0 on the left hand side this time, which means I can multiply both sides by 1 over v2 to turn this quadratic equation into a linear equation. This is going to cancel out one factor here, this factor here, and one factor here. So what you end up with is 0 is equal to, so I guess let me combine some of the like terms here. I have 1/2 m2, factor that out front, and I have this term, m2 over m1, plus, I guess this is 1. And then v2, factor it out to the right, minus m2 v naught. So this is a now linear equation. I can solve this for v2. Let me do that. v2 is equal to, moving this over, m2 v naught over 1/2 m2 over m1 plus 1. Yeah, and I can simplify this a little bit, make it look prettier, cancel this out, maybe multiply numerator and the denominator by 2 m1. I'm trying to get rid of nested fractions. And when you do that, you end up with, okay, 2 m1 v naught divided by, so 2 cancel that out, m1 distributing it in, I have 1 times m1, so 1, plus m2 over m1 times m1, so m2. This is my beautiful expression for v2. I didn't have to use any quadratic formula, it just worked out. And again, this is the potential complication working through algebra involving elastic collisions. It really does come down to these squares, and I can't tell you a good systematic reason why the second approach worked while the first approach resulted in this super ugly expression. There isn't some good rule of thumb I can give. Other than that, I've done this particular version enough times to know that when I see this, specifically when I see this v naught with no other coefficient in front, I knew that this cancellation was coming. And trial and error is really the way to navigate through here. So, okay, I'm actually not done. So I have this v2, and I have to plug that into my boxed expression here to get my v1. And there I can get some result and take a look at it and hope that it makes sense. So this is equal to v naught minus m2 over m1 times this expression for v2, which is going to be 2 m1 v naught over m1 plus m2. You see some cancellations. M1s cancel. So, and I think there's a further simplification I can do. So I can factor out the common factor of v naught times, I have 1 minus m2 over m1 plus m2. And there's a technique for simplifying expression, 2 m2. Technique for simplifying expression like this. You rewrite 1 as the fraction that has the same denominator. So this 1 should become m1 plus m2 divided by m1 plus m2. That's 1, just written differently. Now you can see some simplification here. this m1 plus m2 minus 2m2, that simplifies. That simplifies as m1 minus m2. This 2m2, cancels out one factor, and then you still have minus m2 left. So with all of that simplification, this is my final simplified expression for V1. V1 is equal to V0 times m1 minus m2 over m1 plus m2. And here's the reason I would recommend that you practice simplifying expressions. This simplified expression gives you some insight into what you saw happening. So with the simulation, you saw that depending on how these methods compare, M1 either bounces back or it doesn't bounce back. And how they compare is basically a matter of how is M2 greater than or smaller than M1. And this simplified expression is saying that when M2 is greater than M1, then your V1 will be negative. And negative V1 means leftward, moving M1 after the collision. So that's the analysis of this particular elastic collision. That can be a lot of fun to work through and a lot of good practice. And yeah, that's it. Let's see what else here. There's actually a second solution that I've kind of ignored, I think. So the second solution that I've ignored is, I guess, this is the place where it got wrapped under. So depending on who you had for your math classes, algebra classes, I know I've had math teachers when I was a student who would have frowned at operation like this. You have to recognize that when you do division like this, you are excluding a potential solution. So this implies that you are assuming that V2 is not equal to 0, because if it is, you can't divide by V2. And go back, see if you can get a solution with V2 equal to 0. The answer is yes, you can. And the solution you get, it matches up with, basically imagine if this ball just passed through M2. That's basically what the solution with V2 equal to 0 is. And I'm pretty sure if you work through this other one, plus minus, one of the solutions ought to be like V1 is equal to V0. And so there are actually two possible values of V1. So one of them corresponds to when the collision actually happened, and the other one corresponds to when they missed each other and collision didn't happen. So, yeah. Now, so this is the analysis with elastic collision. So, so the question that I want to ask is, what changes when this is inelastic? What constraint goes away? And when it is inelastic, the thing that goes away, by definition, is the conservation of kinetic energy. The moment someone says something is inelastic, you cannot use this anymore. You have to be given more information. Either someone will tell you how much energy is lost. That might be a one way they can tell you. Then in that case, you might set up a modified version of this. You would say, oh, there's some difference that you need to account for. Maybe that. But the moment someone says inelastic, before any additional information is given, you have to get rid of your conservation of kinetic energy expression. That's one of the constraints that go away. Now, with that, if you are looking at conservation of momentum expression, what you will see is that we have an issue, because we have only one equation remaining, but we still have two unknowns, V1 and V2. So we don't have enough information. And this is where, for a general inelastic collision, where you don't know how much energy is lost, the question really have to give you additional information. They might tell you how much V2 is after collision, or they might tell you how much V1 is after the collision. The question has to give you one additional piece of information so that you don't have more unknowns than your number of equations. Now, completely inelastic collision is different in this way. So with completely inelastic collision, the information that you are given, which won't always be spelled out for you, is this, that V1 is equal to V2. You can see it here. In completely inelastic collision, I guess their masses don't have to be the same. In a completely inelastic collision, after they collide, they stick together and move together. So V1 is equal to V2. So that's the additional piece of information that a completely inelastic collision gives you. And on the topic of the thing that we started this discussion with, which is why can we just say the final kinetic energy is zero? What constraint remains? Well, this is the constraint that remains. Your momentum conservation, everything that we said for momentum conservation, still there, even for completely inelastic collision. So you are still under the constraint that the momentum must be conserved. So that's because momentum is conserved, that's why it's not possible for this to be equal to zero. Because if the final velocities are zero, especially in a situation where you have some initial momentum, then 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 your momentum won't be conserved. That's why these final velocities, they cannot be zero. So completely inelastic collision is really the situation where you lose the most kinetic energy that you can lose under the constraint where the momentum is conserved. So in fact, if you set up this experiment so that you have a zero initial momentum to start, you can actually see all of the kinetic energy go away. So let me just set it up this way. Oh, I can't quite tell. Let's see here. So 0. Okay, so I want this value to 0.5. All right, so I set up these two balls with an equal and opposite velocity so that their total momentum will be zero. Let's see. After they collide, yeah, they come to a complete stop and kinetic energy is equal to zero. So that's the constraint that remains for completely inelastic collision. So I want to approach the completely inelastic collision slightly differently. So instead of questioning why do we have any kinetic energy left, which was the question I was asking this time, let me imagine this hypothetical scenario. You have a setup, and the question doesn't tell you anything about elasticity of collision. But what they tell you is that after the collision, two things stick together. So in some way, the question might not make any statement about conservation of energy. The only thing that it tells you is that after the collision, the two things stick together. And what I would tell you is that if the question has told you that two things stick together, they have told you that this is completely inelastic collision, and you can actually prove that energy is not conserved. So you don't have to assume it. You can just solve the question with the given information and prove that energy is not conserved. This is how you do it. So I think I can reuse most of it because the math will be substantially simpler with completely inelastic collision than elastic collision. What? So let me do the analysis of. Let me not call it completely inelastic because that's maybe biasing it. Let me just say analysis of sticking collision. So somehow in the question, you are told that two things stick together. And so I'm not going to invoke conservation of kinetic energy, for one, because I'm not told that energy is conserved. So if I'm not told something is conserved and I don't have any reason to justify that it's conserved, then okay, then I'm not making use of that. But I do know it is a collision where internal forces dominate. So I can still say, okay, momentum is conserved. So let's start there. With the conserved momentum, then what I have from this information that two things stick together is that I don't have to write out this after collision picture with two different velocities. Instead of having V1 and V2, I can say, oh, it's just going to be V1 and V1, or simplifying it even further, it's going to be M1 plus M2 times V1. Then it's really simple. I have one unknown, one equation. I can solve for it. So let's do that. So my solution for V1 is, well, let's solve V1 is equal to M1 divided by M1 plus M2 times V0. That's it. That's my answer. I'm done. So with that answer for V1, let's explore what happened to the kinetic energy. Was kinetic energy conserved after all? Or can we show that our kinetic energy must have changed? So our kinetic energy before is the kinetic energy of M1. That's kind of easy. It's 1/2 M1 V0 squared. Okay, let's work out kinetic energy after. So for kinetic energy after, we can treat the whole combined blob as one thing. So it'll be 1/2 the total mass, M1 plus M2, times the speed V1 squared. And let me plug in this expression for V1. Then what I have is M1 squared over M1 plus M2 squared times V0 squared. And there's a lot of common terms here, 1/2, one factor of M1, and V0 squared. All those are common, so we can look at the things that are different between the two lines to see how the kinetic energy, if it changed. So let me just cancel this out with the one factor here. So really comparing the two expressions, what it looks like is kinetic energy after is kinetic energy before times a factor. And the factor will be M1 divided by M1 plus M2. And you can stare at this ratio for a bit and realize, if M2 is anything other than 0, as in if this mass exists, then this ratio is going to be less than 1. So your kinetic energy after the collision is going to be less than kinetic energy before the collision. Kinetic energy is not conserved. In the scenario that you saw before, where M2 is equal to M1, in that scenario, you see that this ratio will become 1/2, and that actually explains why our kinetic energy was going down to 1/2. And in the limiting case, where if M2 goes to infinity, or, if, I guess, so that I'm not invoking infinity, in the limit where M2 is much, much, much greater than M1, then you see this ratio approaching 0. So if M2 is like a very large mass, like a wall, then M1 goes to it, sticks to it, then all of the kinetic energy goes away. When a mass sticks to a wall, it's stopped, nothing's moving, all the kinetic energy is gone, and you can get that. It just takes m2 being much bigger thing than m1. So that's the completely inelastic or sticking collision, and you can see that even without someone telling you that there's something that dissipates away energy, if you have a kind of collision where things stick together, it just through this analysis, it must mean that energy cannot be conserved in a situation like that. So, this is where I was working through this and pretending, oh, I'm having trouble with the algebra. And then ChatGPT told me this. For elastic collisions, there's a useful relative velocity relationship. This. And, when you first look at it, this just looks way too simple. You think, that can't possibly be right. And apparently it's right. And I did find the derivation of this relationship, not in our textbook. Our textbook doesn't seem to cover it, but it's definitely in the textbook that we used to use, Giancoli. And it's also in the textbook that I learned my own lower division physics out of, Young and Friedman. So you could say that I should have known that such a relationship existed, and either I skipped over the textbook section, or if I read it, I just forgot it. So let me take some time today now to actually derive it and just to talk a little bit about how I think you should use it in your problem solving. And actually, I might redo some of the homework help videos in future semesters using this relationship because it does make the algebra much simpler. So let me quickly go through the derivation, because once you know what you're doing, as I do now, the derivation is actually pretty simple. So let me write down the title of what I'm driving. Relative velocity relationship for elastic collisions. And I don't know if there's a standard name for it. This is the name that ChatGPT was using, and since I learned it from ChatGPT, let me use ChatGPT's word for it. And I guess I could refer to the derivation that's done in Giancoli or Young and Friedman textbook, but then there's a copyright implication. So let me do an independent derivation here so that I can share this without worrying about someone else's copyright. So we are considering a very general situation of an elastic collision. You imagine 1D elastic collision. You imagine having a mass m1 coming in with some initial speed v1 and striking m2, which has some initial velocity v2. And I've drawn everything to the right, but these could be going to left, then you would just let the velocity be negative. So this is the before picture. And after the collision, there's a final picture of, so after the collision, M1 will be moving in some way. Let's say it's still going the same direction. And let me call this V1 prime. And M2 is doing its own thing, moving at some speed. Let me call this V2 prime. And that's the post-collision picture of the setup. So when you are analyzing this setup, you can use conservation of momentum and energy, like conservation of momentum, like any collision that you have seen. So let me write that down. That says the initial momentum is equal to the final momentum when you add up everything. Rewriting this schematic relationship in a more concrete terms, in terms of the variables we have, what this is the sum of the momenta, m1 times v1, plus m2 times v2. Again, this is completely general. If the particles happen to be moving to the left, then you just let v1 and v2 be negative. Completely general. You say that's equal to their total momenta after the collision. m1 times v1 prime plus m2 times v2 prime. I'm using prime just so the writing is not so colored down in the subscript area. So conservation of momentum. Now, because it's an elastic collision, we can also say conservation of energy. More specifically, conservation of kinetic energy. That's really what elastic means. if there's like potential energy involved, we usually wouldn't call it elastic collision. But even though, total energy might be conserved. So with the conservation of kinetic energy, what we should say is the total initial kinetic energy is equal to the total final kinetic energy, or making it more concrete with the expressions we have. That means 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Now, so before I was using these equations directly, trying to solve for some things that are being asked for. Today, my goal is different. My goal is to derive this relationship here. And actually knowing the form that we are getting to, it's helpful because it becomes a hint to which way we should go. So I'm noticing that it doesn't have masses. So whatever derivation steps I'm going through must somehow cancel out masses. And I noticed that this is actually the surprising and useful thing about it. This is linear in order. That's what made me initially think that couldn't possibly be right, because we have this quadratic thing in energy expression. So that's what was making math difficult. And so in the derivation step, somehow we must be getting rid of these exponents. And what that means is there might be some factoring involved as we are going through the derivation steps. So let me go through some steps that are motivated by these features of the expression that we are getting to. So the number one thing that's motivated by the fact that they don't have masses is I'm going to try to collect them in like terms, in terms of masses, so that I can factor out the mass and see how there might be some cancellation. So I'll collect all the m1 terms on the left-hand side and all the m2 terms on the right-hand side. Let me do that for momentum. Then I get m1 v1. I'm moving over m1 v1 prime, so minus m1 v1 prime. And I'm moving over m2 v2 to the right-hand side to get m2 v2 prime minus m2 v2. All right. And let me do the same thing with the kinetic energy expression. I'm going to collect all the m1 terms on the left-hand side, all the m2 terms on the right-hand side. So 1/2 m1 v1 squared minus 1/2 m1 v1 prime squared, having moved that over. And on the right-hand side, I have 1/2 m2 v2 prime squared, and from having moved this over, minus 1/2 m2 v2 squared. Let's do some simplifications. So I can cancel out some simple numerical factors, like this 1/2. I can just imagine multiplying through the whole thing by times 2. That gets rid of all these factors of 1/2. Don't have to deal with them. And I guess I should factor out the masses so that I can see best how it might cancel out. So let me do that factoring. Let me organize my expressions a little bit so that I have a little more space. All right, so now I have enough space down here. Let me write down the simplified expression. So from this equation 1, I'm going to have this 1 prime. With the m1 being factored out, I have n1 times v1 minus v1 prime is equal to m2 times v2 minus v2 prime minus v2. And from my equation 2, factoring out m1 and m2 again, I have 2 prime, which will be m1 times v1 minus v1 squared minus v1 prime squared is equal to m2 times v2 prime squared minus v2. Now, as you stare at this, I hope you remember some useful factoring relationship that you might have learned in college algebra. If you have expression like a squared minus b squared, this can be factored into this form, a minus b times a plus b, which means this can be factored into this form. So this being a, this being b, it will be v1 minus v1 prime times v1 plus v1 prime, and this can be factored in a similar way, v2 prime minus v2 times v2 prime plus v2. Hopefully that sounds familiar. Now, if it doesn't sound familiar, then you can verify. Take the expression here, expand it out. You will see cross terms cancel, and you'll be left with a squared minus b squared. So I'm going to make use of that because this is what I'm noticing. I'm noticing that this term here that I'll get out of factoring this is going to be equal to this, so I can cancel it. This I get out of factoring this will be equal to this, so I can cancel it. So if I write down something that looks like 2 prime as an equation divided by 1 prime as an equation, then this is what I get. I'm just going to write down the factored version. So it will be m1 times v1 minus v1 prime, v1 plus v1 prime, divided by the left-hand side of the 1 prime equation, m1 times v1 minus v1 prime is equal to the right-hand sides, m2 times v2 prime minus v2 times v2 prime plus v2, divided by the right-hand sides of the other equation, m2 times v2 prime minus v2. So a lot of things cancel out. I get the masses canceling out. That's what I was looking for, so that my final expression won't have masses. And this is the part that makes my final resulting equation linear in order. This one, linear dependence on velocities, cancels out from the factored expression. So you are just left with this final expression, which is wonderfully simple. That v1 plus v1 prime, that is the sum of the velocities of the object 1 before and after, minding the directions. If it's somehow moving to left, then you make it negative. That's equal to v2 plus v2 prime. Now, it's in a slightly different form from how ChatGPT had it, but I think I actually like this form better. Like, I think I can remember this a lot better. Sum of velocities of one object is equal to sum of velocities of the other object. And its usefulness in problem solving is, imagine you are trying to work out velocities of some objects after an elastic collision. So doing it in a traditional way, you might use these two equations. And with this equation being derived out of those two, this is what it means. Between these three equations, conservation of momentum, conservation of energy, and finally this expression that we just derived, v1 plus v1 prime is equal to v2 plus v2 prime. Between these three equations, you have two independent equations. So if you have two unknowns, you can solve for them by picking any two out of these three equations. And before, when I was trying to solve those questions using conservation of energy, I had to deal with these square terms that always made my algebra complicated. But if I now instead of the conservation of energy expression, if I pick conservation of momentum expression and this relative velocity expression, then between those two equations, they contain all the information that was in the original set of equations. So without explicitly using conservation of kinetic energy, using this in conjunction with the conservation of momentum already puts in the information that's coming from conservation of kinetic energy. And in doing this algebra, I never have to square anything. Everything remains linear. I feel a lot more confident working this system of two equations than having to deal with the squaring and whatnot. And if you are a skeptical person like me, you might look at it and think, that sounds too good to be true. What's the catch? I will tell you what the catch is, because there is a catch. And in fact, I did something that your math instructors would disapprove of. This cancellation that I did here, it's improper. I shouldn't have done it, because there's a possibility that this is 0, and I'm not allowed to divide by 0. So, or, flip it around. By doing this cancellation, I'm implicitly saying that this is true, or to be more precise, the mathematical operation I did is invalid unless this is true. So this must be true for me to not have done something naughty. So this v1 minus v1 prime must not be 0, which means we must have v1 not equal to v1 prime. And v2 prime minus v2 must not be equal to 0, which means v2 prime must not be equal to v2. Now, consider looking at this. What kind of solution do you have when v1 is equal to v1 prime? And what kind of solution do you have when v2 prime is equal to v2? It's the trivial solution. It's the solution where nothing happened, where two things are colliding and they just pass each other. So initial velocity of an object is equal to its own final velocity. Initial velocity of another object is equal to its own final velocity because they didn't collide, they just passed through each other. So in using this relative velocity equation, you are losing some information. You are throwing out this possible solution that's a mathematically valid solution that you could have had. But it's the exact solution you don't really want physically anyway. It's the trivial solution where nothing happened. So yeah, there's a catch, but that catch is the kind of catch that we are actually happy with, because it means we don't have to deal with that redundant extraneous solution that we were going to throw away anyway. So that step is done automatically in this derivation step. So this is the relative velocity relationship. Again, many standard textbooks do actually derive it. Giancoli and Young and Friedman, those are the two I checked. So that does it. OpenStax for some reason doesn't do it. But I do think this is a useful formula to have memorized and possibly use it when you see elastic collision problem that could be difficult. And I might actually redo a lot of my lectures on elastic collision using this relationship, because I gotta tell you, I've been doing physics for over 20 years, and this is something new I've learned that I should have learned 20 years ago. So it's describing an elastic collision between two bumper cars. Here's one car, or you can think of them in terms of the carts that you have worked with in the lab. So I have one bumper car and another bumper car, and what the problem is describing is an elastic collision between them. So this bumper car is moving at some speed of v1. So here, this would be this one, leading bumper car, v1. And this bumper car is going at speed of v2. And for this to make a physical sense, not just a mathematical sense, v1 needs to be smaller than v2. And it is, it will be. It's programmed that way. So because of v2, so I said the v1 is smaller than v2. v2 needs to be greater. So v2 needs to be greater than v1 so that the trailing car will catch up. They will collide, and after collision, something will happen, and they will go their way. All right. So I guess we'll get started. So you should have some physical sense, physical intuition for this collision. And this is one intuition you kind of need to have developed going through chapter 9, is that momentum, or more precisely, total momentum is almost always conserved in collisions. There might be some exceptions, especially if you're leaving out interacting objects, like you have a ball that's colliding with a wall and you ignore the momentum of the wall. Then sure, you have external force that's pretty big, so momentum is not conserved. But as long as you, that's why I inserted a total. As long as you're looking at total momentum, even when there's some interaction with the outside bodies, in a collision, typically the impulse due to the forces, external forces, will be negligible. So you can say that total momentum is conserved. So that's one starting place. So I'm hopefully it's kind of obvious. I'm trying to use conservation law strategy because, as I was saying earlier, it's so much easier if you can solve a question using conservation law. So, so the steps in answering question A and B is what are conserved quantities, and the discussion, the mini discussion we just had, is getting you to say, oh, momentum is almost always going to be one of the conserved quantities in collisions. One, Arabic numeral. Momentum is very often going to be conserved quantity in interactions that we choose to describe as collisions. And now you can write out, so you don't have to do the whole thing. You can kind of look at, all right, momentum is conserved. Let me use that information and write down the conservation of momentum expression. Then what that looks like is, let me give the letter M for this. The initial momentum is mv1 plus mv2. So conservation of momentum means this is equal to the final momentum after collision. So same mass, and then this is V final 1 plus V final 2. And this is where I hope you realize that, oh, too many unknowns. I have two speeds that I need to figure out after the collision. And I have only one equation. So that means you need to find one more equation, one more piece of information that will allow you to finish solving this question. So you kind of look for that, and this is where you kind of have to know the what I call physics code words. It's a very specific vocabulary. It gives you very specific and useful information about question. Here, that vocabulary word is elastic collision. So you need to know what that means. It means collision that conserves kinetic energy or conserves mechanical energy. I think we usually mean kinetic energy. So we need to use conservation of energy. In this particular case, especially kinetic energy. So yeah, let's write that out. Then writing this out, we have 1/2, let me erase that, and V1 squared plus 1/2 and V2 squared is equal to V final 1 1/2 and V final 1 squared plus 1/2 and V final 2 squared. And you just have to work through the algebra. And let me write down an expression that's more generic so that you can cover this second scenario with the same equation. So the equations I've written down here, they kind of assume something that's true for part A, so you can use it for part A, but it's not going to be true for part B. So in the interest of at the cost of losing some elegance, let me write in some subscripts so that I have a generally true expression. So instead of having one mass M to represent both masses, so in the second case, I basically just need M1 and M2. So I've already started labeling 1 and 2. So let's use this here. M1 and M2. M1 and M2. M1 and M2. So the reason I'm doing this now is because if I hadn't done this, then I would have been tempted to cancel out masses. And you can do that for part A. That's a good math practice. But for part B, you're going to have to put those masses back in. All right, now some things do cancel out in both cases. This 1/2 cancels out in all of the cases. So let me just get rid of this so that we are at least dealing with a little bit cleaner expressions. And this is what I like to call just math. So once you've written down this set of two equations and verify that, that these two equations encode enough information for me to be able to solve for this system of equations, all the unknowns that I'm interested in, then your job as a physicist is done. But it is still nonetheless true that there's quite a bit of tedious algebra that you still need to complete. And I do encourage you to build up your algebra muscle, do the algebra, and kind of practice. Practice makes perfect. So while I do encourage that, sometimes it's nice to be able to just look up the answer. For one, to see if we are making any mistakes. That's one. For two, I do this a lot when I'm writing these questions. I don't want to do the algebra. I know how to do it, and so I want to show you one tool that can help you cut down on this. What can become tedious? So it's only a tedious work if you know how to do it. So please do learn how to do it. And while you're learning how to do it, it's beneficial to be able to kind of look up the answer. So now this is something that's available to you only for homework. So because for the exams, you'll need to be able to do this by hand. That's why I keep saying to learn how to do this by hand. But while you're working on homework, let me show you one tool you can use to kind of help you check your answer, to minimize the unnecessary frustration. So this is a free version of what is available on something called Mathematica, or you might have seen it as Wolfram Alpha. So this is a kind of free version of that. It's called the software is called SageMath, and there are different ways of getting at it. This particular website, sagemath.sagemath.org, is the kind of least hassle-some way of getting at it. I also have Sage installed on my computer, which I could have used it to demonstrate, but most people don't have, if you have to install something on your computer, then it becomes very tedious. So let me not do that. So there's a function in Sage called solve. So let me just show you, help solve. So that's the help file, tells you how to solve. So what I'm going to do is I'm going to use this computer algebra system to just have it solve this system of equations for me. So I read up on the syntax earlier so that I can do this now. Now I need to define the variables. So I think I had the syntax here, var, okay. So I need to define my 1, 2, 3, 4, 5, 6 variables. That those are M1, M2, V1, V2, VF1, VF2, Those are bars. Bar or bars? I keep forgetting. Bar. Okay. M1. I don't know why this is necessary. I don't know Sage all that well. I used Mathematica for a lot longer, so I know Mathematica better, but this is free. Free forever. Okay, so those will define these symbols as variables so that program won't get confused. Now what I need is to specify this solve expression. It kind of works this way. This expression here defines the system of equations you're trying to solve, and these are the variables you're trying to solve for. So let me write it down. Solve. My first equation is the, well, first equation. M1 times V1 plus M2 times V2 is equal to, I need two equal signs. That's, it's an assignment versus a comparison operator. Let me not get into that. M1 times V final 1 plus M2 times V final 2. And that's my first equation. I need my second equation. M1 times V1 squared plus M2 times V2 squared is equal to M1 times V final 1 squared plus M2 times V final 2 squared. All right, that's my system of equations. And I'm wanting to solve it for V final 1 and V final 2. Let's see what it does. Evaluate. And if I were to try to do this by hand, it would have taken me probably 10 minutes, especially if I'm talking. If I'm just writing as quickly as I can, I might do it faster. But if I'm talking, I'm going to take at least 10 minutes. This did a lot more quickly. It took me more time talking. Now, it gives you more than one set of solutions, and the first solution probably has you going, oh, duh. Duh in the sense of if these two cards kind of just they kind of just missed each other, as in the trailing card just went past the leading card, then all right, that's still an interaction that conserves momentum and energy. So the mathematical solution includes that possibility, which we are going to ignore. We're not looking for that. We did say they collided. So this is the answer that we are looking for. This is the expression for the final velocity of the originally leading card. And so this complicated expression is, you can do some sanity checks by imagining what the expression would be like if M1 is equal to M2, and I'll leave you up to that. It'll give you some interesting result that's worth thinking through, see if that makes intuitive sense. But in the general case where M1 and M2 are not the same, well, this is the answer to the speed of the leading bumper car, and this is the answer to speed of the trailing bumper car. And this computer algebra system did it a lot faster than I could do it by hand. And this is good for kind of looking up an answer that you can refer to in case you are making some trivial algebra mistakes, and that's preventing you from getting the right answer.